So today, we're going to take a journey through the body's own superhighway, this incredibly complex, non-stop network that keeps every single one of us alive and ticking. We're going to dive deep into the engineering of this system, from its amazing central pump to the vast network of vessels, and even the support systems that keep it all running. And we'll be focusing on the key concepts you absolutely need to know for your exams and, of course, for your clinical practice.
Ever stop to think about that? How does your big toe get the oxygen it needs to wiggle, like right now? Well, the answer is all about this incredible delivery network that's so vast, if you laid it all out end to end, it would actually circle the Earth more than twice. We're talking over 60,000 miles of vessels packed inside of you. It's a logistics system so efficient, it honestly makes our own modern superhighways look pretty simple.
So to really get a handle on this system, I want you to think of your body as this bustling metropolis, just filled with trillions of cells. The circulatory system, that's its critical infrastructure. It's the transport network delivering oxygen and nutrients, it's the sanitation department removing waste, and it's the highway for the body's own defense forces.
Okay, so what you're looking at here is the basic map of that superhighway. It's one continuous loop. You've got the heart, which pumps that oxygen-rich blood out through these large arteries. Now, those arteries branch into smaller and smaller arterioles, which then feed into this microscopic network of capillaries. And that's where the real action happens, right at the cellular level. From there, the deoxygenated blood starts its trip back through tiny venules, into the larger veins, and right back to the heart to do the whole thing all over again.
You know, every great transport system needs a central hub, right? A powerhouse that drives the entire operation. Well, in our body's metropolis, that's the heart. And it's not just a simple pump. It's the tireless, precision-engineered mission control for the whole show.
And what an engine it is. It's tucked away safely in the mediastinum, right between the lungs. It's protected by something called the pericardium, which is this tough, double-layered sac that also keeps it from overfilling. The wall of the heart itself has three distinct layers. You've got the outer epicardium, then the thick, powerful middle layer called the myocardium. This is the actual cardiac muscle that does all the contracting. And finally, the inner endocardium, which is a super smooth lining that makes sure blood flows right through without clotting.
Okay, let's zoom in on the layout of this incredible pump. The heart is divided into 4 chambers. You have 2 atria on top, which are kind of like low-pressure receiving rooms for blood coming back to the heart. And then you have 2 ventricles down at the bottom, and these are the powerful, high-pressure dispatch centers. So let's trace the exact path a single red blood cell takes as it travels through these chambers.
All right, follow the journey with me. Deoxygenated blood from the body comes into the right atrium. From there, it passes through the tricuspid valve into the right ventricle. The right ventricle then contracts, pushing that blood through the pulmonary valve and into the pulmonary artery, which heads off to the lungs. After it picks up a fresh supply of oxygen, the now oxygenated blood returns to the left atrium. It flows through the mitral valve into the left ventricle. And notice how much thicker the wall of the left ventricle is. That's because it needs to generate a huge amount of pressure to pump that blood through the aortic valve, into the aorta, and out to the entire rest of the body.
So this whole mechanical and electrical sequence, that's what we call the cardiac cycle. Systole is the phase when the heart contracts, and diastole is the phase when it relaxes and fills up. And that lub-dub sound you hear with a stethoscope, that's super important clinically. The first sound, lub, is the sound of the mitral and tricuspid valves closing as the ventricles start to contract. The second sound, dub, is the sound of the aortic and pulmonary valves snapping shut as the ventricles relax. It's the sound of the machine working perfectly.
All right, so the heart's done its job and sent the blood on its way. But where exactly is it going? Well, it's entering that vast network of blood vessels we talked about. You can think of this network as having these big, high-pressure arteries, like our major highways, and then these tiny, delicate side streets where all the really critical deliveries and pickups actually happen.
This chart really nails the key differences. Arteries carry high-pressure blood away from the heart, so it makes sense that their walls are thick, muscular, and elastic to handle all that force. Veins, on the other hand, carry low-pressure blood back to the heart, so their walls are thinner, and this is a key difference. Many of them have these little one-way valves, especially in our legs, to stop gravity from pulling the blood back down.
You see, the arteries and veins, they're really just for transport. They're the highways. The entire purpose of this whole journey, the exchange that keeps every single cell in your body alive, well, that happens at the microscopic level, right in the middle.
And these are the capillaries. Their walls are incredibly just one single cell thick. And this isn't a flaw, it's brilliant design. This super thin structure creates the perfect place for diffusion to happen. It's right here that oxygen and nutrients leave the blood and enter the tissues, and at the same time, carbon dioxide and other waste products move out of the tissues and back into the blood to get hauled away.
So, you might think this circulatory system is perfect, right? Well, it's amazing, but it's not flawless. It's actually a little leaky, constantly letting some fluids seep into the surrounding tissues. To manage this leakage and to provide some immune security, there's this crucial parallel network, the lymphatic system.
The lymphatic system is an absolutely essential partner. Think of it as a one-way drainage network that mops up all that excess fluid that leaks from the capillaries. This fluid, which is now called lymph, gets transported through lymphatic vessels. Along the way, it gets filtered through lymph nodes, which are just packed with immune cells. These nodes act like security checkpoints, detecting and destroying any pathogens they find. Then, the clean fluid gets returned to the circulatory system, which keeps our blood volume and pressure stable.
Okay, so let's zoom out again and look at the whole big picture. Because this isn't just one highway loop we're talking about. It's actually two distinct circuits, the pulmonary and the systemic, and they're working in perfect continuous harmony. First up, you've got the pulmonary circulation. Think of this as the short trip. The right ventricle pumps deoxygenated blood just to the lungs to pick up oxygen, and then that fresh, oxygenated blood comes right back to the left atrium. Simple. Then you have the big one, the systemic circulation. This is the high-pressure grand tour, where the powerful left ventricle pumps that oxygen-rich blood out to every single other part of the body before the deoxygenated blood makes its way all the way back to the right atrium. But you know what's maybe the most incredible part of all this? The entire system is self-powered. The heart has this amazing property called autorhythmicity. What that means is it actually generates its own electrical spark to beat. It starts in a little cluster of special cells called the sinoatrial node, or SA node. That's the heart's natural pacemaker. And that impulse then spreads through a specific conduction pathway, making sure the heart contracts in a coordinated, effective rhythm, all on its own.
So this whole metropolis of trillions of cells relies completely on these highways being clear and unobstructed. And that leaves us with a really critical clinical question. What happens when those highways get narrowed by something like atherosclerosis, or worse, get completely blocked by a clot, leading to devastating traffic jams like a heart attack or a stroke?